second talk, I'd like to prove the volume conjecture. Remember that this is not a proof. Quite far away from genuine proof. But I hope I can tell you why we, or at least I, believe that the conjecture is true. First of all, I think it's helpful for you to tell you a practical way to calculate the color-Jones polynomial. First, I review the definition. I use this complicated R matrix and its inverse, and curly bracket M is this, and factorial of curly bracket is defined as usual. And R matrix corresponds to a positive crossing, and R inverse corresponds to a negative crossing. And so this is the definition. And to get T, I hope you remember that we replace each crossing with R or its inverse and define homomorphism from the top to the bottom and take the traces. So, and for practical calculation, we don't need to take all the traces. We don't need to close all the arcs, but we leave one without closing and take the other n minus 1 arcs. And this gives a homomorphism from C to the n to itself, but it is a scalar multiple. This is due to Schur's lemma. So we only want to know which scalar is multiplied by taking this homomorphism from C to the n to itself. And to do that, we fix a basis E0 to AE n minus 1 and take any EI to know the multiple, the scalar multiple. This is because, so if I denote mu by this operator, it's a linear operator on C to the n, and by definition, we need to put mu here and close it. That is, we put mu here and take the trace 1, which is a usual trace, the sum of all the diagonals. And this is just an adjustment. We can ignore this. And this is because mu is a scalar multiple, so it is diagonal. Phi is diagonal because it is a scalar multiple by Schur's lemma. And mu is also, in this case, this is also a diagonal. So we just simply take the scalar multiple times some constant, not a constant. This is the value for mu. The ith diagonal is q to the y minus n plus 1 over 2. So, and this is the sum of this power of q is exactly this quantity. So we have S, which is the scalar multiplied by this phi, and multiplied this one, and some adjustment. This shows that the Jones polynomial is nothing but the S, the scalar, multiplied by this homomorphism from B C to the n to itself. So I'd like to give you an example. So we choose any basis E sub I. And another important thing is that from the definition of the R matrix, so for the R, L is I plus n, and n is bigger than or equal to 0. So L is bigger than I, and K is smaller than J. So if we have a crossing, and this indicates we have EI E sub I here, the basis L, and in J, then L is bigger than I, and K is smaller than J. And from the definition, we know that I plus J is equal to K plus L. And similarly, for the negative crossing, we have I plus J is equal to K plus L, and L is smaller than I, and K is bigger than J. So, I will show how to label these arcs. Label corresponds to the basis. So, any I we can choose, but for convenience, we choose N minus 1. And the point is that if we pass this crossing, L is greater than or equal to this number. So this should be N minus 1, because there's no integer greater than N minus 1. No index greater than N minus 1. So this should be N minus 1. Okay. So this is why I choose N minus 1. This can be anything. Just for convenience, we choose N minus 1. And for next step, we choose just any I here. And then, because the sum is preserved before entering and after going out, so I is, so here we have I, okay, because the sum is preserved. And we also choose any J here, and then choose K. And because of the sum, so we know that here we have I, and here we have J. So I plus J is equal to something plus K. So we have I plus J minus K here. And similarly, we have N minus 1 plus J minus K here. And because of the sum is preserved, this arc should be labeled by N minus 1. Now, look at this. This crossing. This is negative. So K, this is, yes, this is greater than. Yes. Sorry. Confused. Something's wrong. Anyone, this is greater than or equal to J, so N minus 1, N minus 1 minus K should be positive or 0. So K should be 0. So anyway, we have J should be, so K should be equal to J. So we have this, we don't need any K, so we only have two parameters, I and J. So we have this labeling. So this means that if we start the basis E sub N minus 1, we are going along, and we have again E sub N minus 1. And this homomorphism is just a scalar multiple. And that value is exactly the Color-Jones polynomial, or this Color-Jones polynomial. And then, so, and we associate our matrix to each crossing. So here we associate R, but the index is N minus 1 and I, and N minus 1. And so here we associate R index and R and R index. And we put mu here, so we have mu sub j and sub j, and mu e here. And after some calculation, we got this equality. Any questions so far? Yes.
When
the basis, what?
Can one use a basis where the mu is diagonal?
In this case, mu is diagonal. So if you use other Lie algebra, you don't do this. It's the only case for the colored zones. Okay. Of course, you can do this because if mu is not diagonal, you have to shift the index here. But you can do it similarly. So we have two summations, and we know that I is bigger than j. And it is rather difficult to change it into a single summation. So do not try it. It is too difficult. Anyway, for any link, now you can calculate the color zones by hand. Now, so I will give a proof of the volume conjecture. To do that, we first need to estimate each R matrix. And to do that, we need to know what happens to the quantum factorial at the nth rootability. So from now on, we replace Q with the nth rootability, and I unify zeta sub n. And we often use this kind of quantum factorial. And by definition, this is just, k factorial is just the product of this. And n minus k minus 1 factorial is not exactly this one, but up to some power of zeta, we have this product. So, because zeta is an nth root of unity, we have the product from 1 to this way to n minus 1. So the product of these two is up to some power of zeta. It is equal to 2 to the n minus 1 times products of these signs. And there is a nice formula of this sign, which I hope you can find it somewhere. I don't want to prove it. It might be a good exercise. Anyway, this product is standard V n. So the point is that the product of two factorials is n times some power of zeta. So if we define round bracket zeta sub k plus to be the product from 1 to zeta up to 1 minus zeta to the k, and zeta sub k minus 3 the product from zeta sub n to zeta to the n minus 1 minus k. So this is, yes, the product of it is already here. Then the product of the two is up to some power of zeta equal to n. So yes, note that the k factorial is again something like zeta sub k plus, and n minus 1 minus k factorial is something like zeta sub k minus 1. So here I'd like to say that the k factorial is just k factorial, and n minus 1 minus k factorial is something like again k factorial in a sense. So the R matrix is again up to some power of zeta is of this formula, and which is so as in the last sheet, n factorial is by definition zeta sub m plus, and I factorial is zeta sub I plus, and n minus 1 minus k factorial is what? So by definition this is zeta sub k minus, but zeta sub zeta sub k minus times zeta sub k plus is equal to n. So we can take this down by paying n here. The product of these two is equal to n. So similarly, we have L here, L upstairs, so we have L minus. So this is equal to zeta sub n plus. So to go downstairs, we have L minus here, and n here. And the last one, here we have j minus, zeta sub j minus. So this is just up to a power of zeta and n squared. And similarly, for the R minus, we have a similar formula. So, because the current Jones is the sum of all levelings, the levelings was that I described, and the sum of products of all crossings, and for each crossing we have either R or R inverse. So the current Jones can be written in this form. Okay. And then we'd like to know what zeta sub n or zeta sub n plus or minus looks like. So we take log, because zeta sub k plus is a product of 1 minus zeta and so on. So we take log of these. Then this is just a sum of log of these. And and zeta is the nth root of unity. So we replace j over n with x. Then this is a very rough estimation. Don't believe me. This is not a proper approximation. But very roughly, because yes, this may be okay, but this double cube means a very rough approximation. And this is something like integral. I think it is okay. And we again replace exponential of this one with y, then we get something like dilogarithm. So the dilogarithm was defined by Taylor, so I don't say so much. But this is just the definition. So from this formula, we see that the log of zeta sub k plus is approximated by this, by using dilogarithm function in terms of zeta to the k. And similar is true for k minus. So we finally have zeta sub k plus minus can be approximated by exponential of dilog. And here we drop dilog of 1 because we'd like to know the asymptotic behavior for large n. And this is, yes. So we drop, no. Yes, we drop dilog of 1. So, remember that the color Jones is the sum of products of R matrices, and one R matrix can be approximated by dilog because here. So each of these can be replaced by dilog, and we have some power of zeta and some polynomial of n. So we have this formula. And here we also have log term. And because we have some power of zeta, for example, k squared power of q is of this form, and which can be written dialog of zeta squared. So some log term is here. But essentially, we will look only at dialog functions. Anyway, the point here is that the Kalfagianni can be approximated by sum of labelings of exponential of some dialog functions around, and the labeling are around each crossing. Okay. Remember that we are doing a very rough estimation. So we put this term, we denote this term by V, so V of zeta. And I1 up to IC are labelings on arcs. So remember that for crossing we have 4 arcs. So if we ignore polynomials, so the Kalfagianni can be written as the sum of over labelings of exponential of V function. And because here we have exponential term, so we may drop polynomials of n because exponential grows very quickly. So we may ignore the polynomial term. So after a rough estimation, we can write the Kalfagianni polynomial as the sum of all the labelings of the exponential of n times v function over 2 pi r. So the point is, the essential part is this v function, which is defined using dialog of zeta. And here's a very dangerous approximation. We want to, usually it is very hard to estimate summation. And by technical reason, we want to replace it with integral along some contours. So J1 up to C are some contours. So if we can approximate the Kalfagianni by multiple integrals, it is usual technique to know the asymptotics of the given integral. So we will integrate this quantity, and this is a function of this drop, dz. B is a function of z. And I hope you remember the technique I showed you for the figure note. And in the case of the figure note, the Kalfagianni of the figure note is a sum of positive numbers. And we found the maximum of the summand, and we use only the maximum to estimate the limit. So we follow that technique. So we want to know the maximum of the absolute value of this term. We want to know the maximum of the absolute value of this exponential. To know that, we want to know the maximum of imaginary part, because this is just the real part of here. So we want to know the imaginary part of this function. Then that would give that would dominate the whole integral by the same reason in the case of the figure. So, but here it is not the case that we can simply find the maximum along the contour that we choose. But instead, we may need to change the contour. Sometimes the maximum occur out of the contours. That is one difficulty to apply this method, so-called saddle point. And anyway, we want to find the point where the imaginary part of P takes its maximum. And we denote that point by x1 up to xc. And usually this is called the saddle point.
What is the significance of the contours?
By Cauchy's lemma, so we can, if V is a good function, we can change the contour. So we don't need to mind. But the point is, we have to know where the singularities are. And we have to avoid it. Yes?
How do you know that there are singularities? How do you know that there are saddle points?
So that's another difficulty. So you talk about this function V? No.
It's a precise question.
Yes.
How do you know that this set of saddle points is not empty?
Okay, so we assume that. Otherwise, yes, there are many difficulties, many questions. That is one question, one difficulty. So to apply this kind of method, we need explicitly the function V. But unfortunately, the number of parameters C is the number of arcs. It is something like the number of crossings, and it will become bigger. So usually it is almost impossible to know the function exactly and know the singularity exactly and know whether the saddle point exists or not, or whether they are far from singularities, and how we change the contours. So remember that we have many contours. So because it is a multiple integral. So we need to know multivariable function explicitly, but it seems to be impossible. So we are assuming many things. So if we are very lucky, we can find the saddle point where and their saddle points are on a very good position, and we can change the contour to pass the so that the contours through the saddle point where the V function takes its maximum. Then we can approximate the whole integral by at a single point. So we want to estimate the integral along some contours of the V function of Z. But once we find the saddle point, then this single value dominates the integral, as in the case of the figure node. So we can say that the Kalfagianni's goes like value. Note that x1 up to xc are constants. So this is just a single complex number. And the asymptotic behavior of the Kalfagianni's is like this quantity. Okay. Now, how to find the saddle point? Because we are seeking for maximum, it is it satisfies these equations. There is a partial derivative. So because it is a maximum for all k's, so all partial derivatives should vanish when it is maximum. Of course, as Stoltzfus said, if there's no saddle point, it is another problem. But we assume that we can find the saddle point in this way. Yes.
My question is,
Yes.
how do you know that these equations, the ones you just wrote down,
Yes.
have a non-empty set of solutions?
Yes. Yes. So so far no way. No.
That would imply generalization of non-confidence.
I don't know. No. So you mean when the
These are the gluing equations, right?
yes. No. Together with the completeness equality.
Those by themselves are the gluing equations. It's a system of polynomial equations.
Yes. Yes. But this
Not the completeness, just the gluing.
really for the 2 pi I think it also contains the completeness. I'm not sure. Anyway, to start with, do you mean that if there's no solution, then it means that the knot is not hyperbolic?
It means the hyperbolic structure does not come out of that planar projection.
Maybe yes. So we fix a diagram. So it may happen that by this technique we can. I'm not sure whether we can always find a solution to this equation. So this is yes.
Maybe it's fair to say that this is a method, so which will
Yes.
sometimes work and sometimes maybe not.
No.
Uh,
Yes,
but
you're right.
My question,
Yes.
so I mean that would answer Stamos's question. But my question would be, when does this method actually work? Is there another example than figure 8?
So Yokota said that it works for any alternating nodes. But it is hard. So he said that this equation, this system of equations has solutions when the knot is alternating. But there's another question, which solution we choose. But it's another question.
How can you see that there are gluing equations here?
Here? Not yet. So I'm just talking about the colored zones. So geometry will appear soon. This is just a question of analysis. And I'm talking just very, how can I say, optimistic case. When everything works well, then this would be true.
I mean, my
Yes.
question was really
Yes.
for the figure 8, it's just
Yes.
one-dimensional.
Yes.
So C is 1.
Yes.
And then we can
easily find the maximum.
But if C is bigger than 1,
Yes.
is there an example where it actually works?
No. I think Rinat Kashev and Yokota have some. In the case of 5-2 no.
Where C is 2.
Yes.
Is this actually done?
But not for any case. So there are more cases for when C is 2.
Okay, thank you.
So this is very hard problem. Okay. Any more questions? So once, so if these are true, then because if n is big enough, this approximation holds. So we can take. Sorry, I dropped the log here. If we take a log and divide by n and multiply by 2 by I, we get this. So in this way, we may be able to calculate the limit of the left-hand side. But difficulties, yes. There are, so far, we have many difficulties. But so the first difficulty is, of course, the very first difficulty is just to write down the formula exactly. It is already quite hard. But the next one is to replace the summation with an integral. And which control we choose, it is very difficult because this is a multi-integral. And it is a complex value function. And the next, so how to apply the saddle point method I described in the previous sheet. First of all, the system of equations may have no solutions, or if it has, it may have many solutions, and which yes.
What exactly is the contour, the initial contour?
We have to choose appropriately. So I can tell you no. So there are several techniques we use. Residue theorem there are many techniques to replace summation with an integral. So we have to choose carefully.
So we'll do by.
Yes, something like that. Yes.
And what is the regularity of the?
Sorry?
The function, what is the regularity? Some singularity.
So one technique is just to introduce function and use that residue to replace the summation with an integral. So in the case of the figured knot, it is so simple because everything is real and positive. But in this case, everything is complex. So we need to, it is hard to approximate the summation with an integral. But maybe we use integral around the singularity. And we need to introduce some function with singularity.
What is B look like again? The prime picture, the system reservations that this out point. Could you?
Yes.
Was V defined earlier?
With what? V, yes.
Was it what was the definition of the agent? I seem to have.
Which definition?
V.
Yes.
V.
Yes.
Was it defined earlier in the slide? It was that monstrous
Yes.
thing.
So if you can calculate the Color-Jones property, then you can find V.
I mean, is there an interpretation?
Yes, yes, yes. So this is a, yes, if you can choose V, in a simple, how can I say, if you start with a diagram, you have Color-Jones polynomial, and there are several ways to choose V by using dilog and log. And it depends on that V, how we choose J. And again, we need to choose saddle point. Before that, we need to change the contour J properly. So there are many difficulties to do this. And if we have many solutions to the system of equations, we have to choose one and only one. And it is hard to decide which saddle point we have to choose. Yes.
But the choice of saddle point there should correspond to something like the choice of instant time in Stoltzfus is that's the Color-Jones where he gave several different contradictions. So, and is it possible that choosing a saddle point is not so much a problem as an advantage, that each saddle point corresponds to kind of a different contribution to this asymptotic.
Do you need to, for each saddle point we can.
So I think it's true that at least with the figure eight if you take different saddle points of that thing, you get the three different terms that Stoltzfus wrote on the board.
So for each, we may say that for each solutions to the system of equations, we have something here. So we may say that we should take the maximum of these. But I don't know whether it is true.
So
yes.
actually there are two sets of points.
Yes.
One if you and the other if
So yes, I will tell you later, but each solutions may correspond to some hyperbolic structure of the knot complement, and with some tetrahedron reversed. Anyway, yes.
say for figure 8, but
Yes.
one you're never going to get it this way.
Mhm.
The discrete paper, the complex conjugate, and the trivial.
Mhm.
The trivial you cannot get it this way, but
No.
it contributes
Mhm.
to the couple.
Mm, mm,
And that's,
yes.
for example.
So here we assume that the color Jones grows exponentially. So if this quantity is negative, then it is very hard to say which what kind of asymptotic we want. So anyway, there are many problems. So problems you can attack. So any more questions, comments? So we like to express how this kind of method corresponds to geometry of knot complement. As Dylan described, we want to decompose the knot complement into tetrahedral, topological, and ideal, truncated, ideal. Each vertex are on the infinite sphere. So it is so big. So if we look at the crossing, then we put an octahedron between the top and the bottom, like that. And we can decompose this octahedron into 5 tetrahedra, like this. So you see, this is zeta to the I, and it corresponds to a top left tetrahedron here. And indexed by k, we have this is bottom left, and in the lower position we have this tetrahedron. And indexed by minus j, this is somewhere here. Yes, bottom right and on the lower left. No. So top right and on the bottom. And indexed by m, we have in the middle. So this is here. We have a tetrahedron in the middle of the two pyramids. Can you see? And so the top and the bottom are on the arc, on the knot. Now we pull the other 4 vertices to the top, to the infinite point. Then we get, so these 2 points are on the knot. And these 4 are on the infinite point. And by some procedure, we can remove this infinite point, and we get decomposition of the knot complement. into topological ideal tetrahedron. And each tetrahedron is decorated with a complex number, zeta to something.
Could you say a little bit more about how these octahedra are glued to each other? Right, this is the local picture of one crossing.
Yes. So there are many. So yes, thank you. So I only draw a very local picture, but you have many octahedra, and we need to paste these tetrahedra in a nice way. So we get triangulation of the knot complement. So far it is topological, but each tetrahedron is indexed by this kind of complex number. And here we have M. M comes from the R matrix, and others, I, J, K, L, are from the labeling on the crossing, around the crossing. And in a sense, M comes from this crossing, the difference between the labels, L minus I or K minus J.
And I guess the question was
Yes.
how these octahedra are glued together. So for example, how would the edge, do the horizontal edges correspond to faces? Is that right? So this horizontal edge,
Yes.
what is it glued to at the
So
next crossing?
after putting this to the top and putting down this to the bottom, this will be vertical.
Yes, and so it's in the middle of the face.
Sorry?
So it is in the middle of the face of the
No.
diagram?
This is an edge,
Yes.
and this will become a vertical edge.
Yes.
And we have another edge here, and these are identified.
Because they both belong to the same face of the diagram?
Face of the diagram. What do you mean by the face? This face, you mean?
Yes.
Yes, in a sense, yes. Yes.
So
So for this region of face of the diagram, it corresponds to one horizontal edge.
which becomes vertical.
Yes, it becomes vertex, and it is in a sense it belongs to this region. And around the region, we have many crossings.
That's
we
how
have
they are
many
grouped
edges.
together.
Yes. And then we paste them together.
Does it matter whether the diagram is alternate? Does it work in general?
In general. In general, we can do this. Okay, So the knot complement, if we fix a diagram, then we have decomposition of the knot complement into topological ideal tetrahedron. And then the index is zeta to the ik. Zeta is the nth root of unity, but we want to regard it as just a complex parameter. This corresponds to the fact that when we estimate the color zones, we choose the contour. So we are rather free to choose the contour. So we should be free from this kind of nth root of unity. We replace it with a free parameter, zk. Then each tetrahedron is parameterized by just a complex number, and it corresponds to a complex number can parameterize ideal hyperbolic tetrahedron. Now, so we have knot complement, which is decomposed into ideal hyperbolic tetrahedra parameterized by these C complex numbers. And we want to choose these parameters so that it makes the knot complement. It makes the knot complement a kind of geometry. We do not assume so far that the knot complement is hyperbolic. It can be any, but in a sense we assume that it can have complete hyperbolic metric. Then try to find these parameters so that around each edge the sum of the angles is 2 pi, and this is the gluing condition. And this is the Euclidean completeness condition, so that the truncated triangles make Euclidean torus. And if we have these two, then, curiously, these conditions, together with gluing and completeness condition, these conditions are the same as the system equations as I described before. I think this part can be done without knowing of any Karat-Jones. This can be done independently from the Karat-Jones things. So, I don't know how we can choose a solution. One of the solutions to make the knot complement into complete. There are several solutions. Then one of the solutions may have negative tetrahedron. But we choose a proper solution, then it makes the knot complement into complete hyperbolic manifold. Then the solution, suppose that the solution of these equations coincide with the solution that I described as the limit of the Karat-Jones, then the same parameter gives the, yes.
Can you say again what would it mean? How would I see that the tetrahedron is negative?
This system of equations may have several solutions. And one solution may have tetrahedra, reverse tetrahedra.
But how would I see it?
I don't know.
Parameter would be in the lower half plane.
So Zi is always positive in the upper half plane, it's okay? Is that what you're saying?
Yes. So if you take the complex conjugate, then it will give a reverse one.
Okay,
So the same may be true for the Karat-Jones. And maybe much worse than that in the case of the Karat-Jones. But the system of equations is the same as the Karat-Jones case. Yes?
So if you knew that a certain knot diagram, that the octahedral decomposition was geometric, does that give you the Vulcan conjecture for that diagram?
No. Because we have to know the asymptotic. We have to replace something into integral. That is another big problem. And we have to say that this exactly gives the asymptotic. It is another big
the
problem.
same system of equations,
Yes.
the asymptotics of these equations is still.
Yes.
So what does this mean? It's the same. What's the next challenge? So suppose you knew. Suppose someone handed you a diagram
Yes.
for which that octahedral decomposition was geometric.
Yes. Then we have to first replace the Karat-Jones summation formula into an integral. And then we have to choose contour properly. We know that if we know the solution to this problem, then we know where the saddle point should be. So we may know where the contour should go through, but we should prove it. That is a big problem. Okay. So then I think this is what Dylan told you. So the V function of coming from the Karat-Jones is written in terms of dialogue and some laws. and the volume of the tetrahedron hyperbolic ideal vector parameterized by a complex number Z is almost the same as imaginary part of the title, with some log. The log is not so important here, but it is important anyway. So, roughly speaking, we see that, as I told you, the 2 pi I times the limit is given by exponential of n over 2 pi I times v of x. And v of x, the imaginary part of v of x is equal to the volume of the knot complement. So, if you take the imaginary part of the limit, we have the volume. And this is just I dropped the log here. If you take a log of the absolute value, then the limit is the volume, and which is the volume projection. So I sometimes assume that the knot complement is hyperbolic, but without assuming that, we may have, without that assumption, we have a kind of topological triangulation. And we have some system of equations. And the limit may correspond to the case where, if we solve the gluing condition and the completement condition, we may have a solution which may correspond to torus decomposition of the knot complement, the decomposition of the knot complement into fibered pieces and ciphered fibered pieces. And in, so that would support the volume conjecture for in general case. So that's all. Yeah, thank you.
Are there any other questions?
Yes.
Your knot is hyperbolic. So you know there exists this hyperbolic structure in the complement, and you have this topological. So doesn't that tell you that there is a logical solution at least to your equation?
Yeah, I hope so. I don't know. So, yes.
I asked this question in Dylan's talk, and the answer was no.
Just no.
The answer is not no. Whether you can find the ideal triangulation so that.
Yes.
You can do a 2-3 move to the ideal triangulation of the figure A, to decompose it using 3 ideal tetrahedra. Write down the Green equations and get an empty space of solution. You can do a 2-3 move to the
So
figure A knot
which
complement that
does
uses 2 regular ideal tetrahedra. Replace it by 3 ideal topological tetrahedra. Write down the Green equation and have no solution. Degenerate. I mean,
You sure?
yeah.
But if you put 2 regular ideal tetrahedra together and do a 2-3 move, it works geometrically. So why would the equations not solve?
Topological, a degenerate, one with short arms.
Well, there aren't any. If you've got 2 regular ideal tetrahedra, glue them together along a thing. I think you'd have to do additional moves.
Then you will get the region. After doing it a couple of times,
Yeah.
But there's no corresponding diagram.
You can start with a non-trivial diagram of the unknown and write down the glue equation for that. Can we solve it?
No. Anyway, sorry, but there's no good examples other than the figured knot. And the figured knot is, it is true, but I'm sorry about it.
operation characteristics that the conjecture is
What?
So,
Yes.
forming a volume conjecture is actually a series of estimates and calculations that they can use to form a volume conjecture. Or is there other intuition that volume conjecture?
I don't know.
You should ask Kashai.
Okay, so let's thank Hitoshi again. Next talk at 11:20? Yeah, that's what it says here. What? Who's next?